Hello, everybody. So what we're going to look at today is going to be section 5.2 in the book, part 2. So we're still doing induction, and this is still strong induction. In the next section, we're going to be looking at structural induction, but we are not there yet. So strong induction. So let's go ahead and get started. So what I want to do first is just kind of a recap of what we did last time. We're going to do a very similar proof to the previous proof, okay? Just to get back up to speed on strong induction. So recall, for strong induction, what you need to do is you have a basis step. Actually, let me write strong induction. So for strong induction, proofs, what you do is you have a base step or basis step, and your basis is you're going to show, let's just say P of 1 true. Remember, property P is what you're trying to prove. So you do that. And then for the induction step, what you do is you have your induction hypothesis, which is induction hypothesis, is assume P of 1, P of 2, all of them up to P of k are true. So you get to use all of those as if they were facts in order to prove the thing you need to prove. Hard to write. So you assume that all of those are true, and then you're going to show that P of k plus 1 must be true using those induction hypothesis facts. And then you have your conclusion, which is P of n is true for n equals 1, 2, 3, dot, dot, dot. All right. And so the difference is just in the induction hypothesis compared to weak induction, right? So for weak induction, you just have this P of k. But for strong induction, you have P of 1 all the way up to P of k. And that's the only difference, right? So yeah. And then what we did was we did what I called like a stamp proof, which we're going to do one again, and that's going to hopefully remind us of how this goes. So example 1, we are going to show, we're going to prove every postage, that is 12 or more cents, can be made with 4 and 5 cent stamps only. Right? So that is what we're going to try to prove. Now, I guess just a note before we start the proof, and that is going to be regarding this 12 or more in comparison to the 4 or 5 cents. Remember that the reason it's 12 is because if you have your 4 and 5, if you do 4 minus 1 times 5 minus 1 for the 4 and the 5 cent stamps, that is going to be equal to 12. And that 12 is the 12 or more cents. Okay. And so as long as the 4 and the 5 are what they call relatively prime means that the greatest common divisor of these two is 1, right? So no numbers go into both of these except for 1. All right. So that's just kind of preliminary. You didn't need to know that. You could have just, if they say to prove it, you can prove it. But the homework problems, they don't always give you this, and sometimes they make you come up with it. So it's good to have a formula, and that's why I am making a point of that. All right, so let's go ahead and do this proof then. So this should be exactly like the proofs that we did, or the proof that we did last time, but we should be able to do it faster now. So what's the base step or basis step? So the basis step is going to be, we need to show that it's true for n equals 1. But actually, that's not true for this particular problem, the stamp problem. So remember, what you have to do for the stamp problem is, if the lowest value of stamp that you have is, in this case, 4, you actually have to show 4 values in particular. So if your low stamp value is 4, lowest value is 4, so we need to have 4 values in your basis step. And if you don't remember why that is, we'll talk about it. But the reason, quick version of the reason that you're going to need 4 is because later on we want to be able to say add a 4-cent stamp. And if you start at 12 and you add a 4-cent stamp, you get to 16. And you'll see why that's relevant momentarily. All right, let's just go ahead and do this. So like I said, we need to show 4 different values here. And we're starting at 12, right? Because they say every postage 12 or more. So let's start at 12. So your 12-cent postage, I'll say postage 12, is going to be, how do you get 12? Out of 4 and 5-cent stamps. It doesn't matter how you do it, you just have to figure it out. So with 4 and 5-cent stamps, the way you would get a 12 is you would just have 3 times the 4-cent stamps, right? That's how you're going to get 12. All right, and then you do the same thing for the 13. How are you going to get 13? Well, you can figure it out, but the way you're going to do it is 2 4s and a 5. So you're going to need 2 of the 4-cent stamps, and you're going to need 1 of the 5-cent stamps, and that's 8 and 5, which is 13. So then you do 14. So for 14, you're going to need 2 5s and a 4. And there is a pattern here, but you don't need to know the pattern. You just need to stop and think about it and actually just figure these out, okay? These shouldn't be that hard, to figure out. You've only got 2 different kinds of stamps. You can figure out how to make a 14, right? So 5 and 5 and 4. All right, last one here, 15. How are you going to get a 15? It's going to be 3 of the 5-cent stamps. And there is usually a pattern on these, but it's not the same pattern on every single problem. So don't worry about the pattern usually. But like you can see, what's happening here is that we went from 3 4s to 2 4s to 1 4s to 0 4s. And for the 5-cent stamps, we have 3 and then 2 and then 1, and then there was none when we started. So, I mean, obviously there's a pattern, but like I said, it's not the same pattern in every single one of these proofs. So, don't worry about it. Just know how many of these you need to do, right? Lowest number is 4, so we did 13, 14, 15, a total of 4. We start at 12 because that is what we were told this pattern starts at. Okay, now obviously you could continue on in this fashion, right? Like if I say, how do you make a 16? You could figure out that a 16 is 4 4s, right? And then you could figure out that a 17, like how would you get a 17? You can figure it out, but it should be 3 4s and a 5, I think. Would that do it? Oops, 1 5-cent stamp. So 3 3 3, yeah, that'd be 17, and so on, right? And that keeps going. But we need to prove it for all in, so we can't write them all down, right? We can't write infinity of them down. So we write down these 4, that's your basis step, and then you move on to your induction step. So for your induction step, what you're going to do is assume that k plus 1 is going to be at least 16, right? Because we don't need to prove anything about 15 because we've already got 15. So we assume that all values or all postages from 12, starting at 12, up to k can be made from 4 and 5 cent stamps. Right. Now compare that induction hypothesis to what we set up here. So the induction hypothesis was, from 1 up to k. And I said this in different words, but I said from 12 up to k. So it's still the same thing. I'm just not writing p of, like I could have written p of 12, p of 13, up to p of k. In words, this is how I would write it. So all postages from 12 up to k can be made from 4 and 5 cent stamps. Okay. In addition to that, we can also assume that k is at least 15. Okay. Because we did 12, 13, 14, and 15 already. So we don't need to talk about that. So k is 15 or more. We can do that because we don't have to worry about 12 through 15 because we already did 12 through 15. So we only need to start at 16. Now, you might say like, oh, well, why are you saying 15 if we're actually starting at 16? And that's because what we're supposed to show is, look at your thing here. You assume 1 through k are done, and you're supposed to be showing k plus 1. And so I'm assuming k is 15 or more, and then that way k plus 1 is 16 or more. That's the same assumption, right? So k plus 1 is 16 or more. All right. And now this is where the proof is. Now the proof is honestly identical for every one of these problems, really, right? You just get the numbers right, like the 12, the 15, and the 16 here are for this particular problem. But once you have that, you say, so k plus 1 is 16 or more, and the rest of the proof is just the same, right? Because k plus 1 is 16 or more. So if you add actually, let me say this differently. I want it. This isn't the way you would think about it. It's kind of working backwards, but this is the way I want to write it. So k plus 1 is 16 or more. Now, remember that the smallest stamp is 4. And I'm just writing this off to the side to remind you that this is why I'm going to do what I'm about to do. So k plus 1 is 16 or more. So k plus 1 minus 4 is what? K plus 1 minus 4. That's just k minus 3, right? Is how big is it, though? Well, if k plus 1 is 16 or more, and then you subtract 4, then k minus 3 is 12 or more. I know that there's so many numbers that it's starting to get confusing here. But, k is 15 or more, k plus 1 is 16 or more, k minus 3 is 12 or more. So all of those are consistent with each other, right? It's just a lot of writing. Okay, so k minus 3 is 12 or more. So since k minus 3 is 12 or more, that means k minus 3 is a postage that can be made. Since k minus 3 is 12 or more, and Actually, you know what I want to do? Okay, hold on. Let me think about this for a second here. This is fine, but I feel like there's a better way to write this proof. And so I feel like I want to back it up and do that. Yeah, you know what? It'll be equivalent, so I'm not going to bother. All right. So k plus 1 is 16 or more. K plus 1 minus 4 is k minus 3 is 12 or more. Since k minus 3 is 12 or more. And obviously, it is also less than k, right? So this k minus 3 is in this region from 12 up to k, right? It's less than k because it's k minus 3, and it's bigger than 12 because we set it up that way. So k minus 3 is 12 or more, and less than k, that's the highlighter, is less than k. So by the induction hypothesis, postage k minus 3 can be made. All right. So postage k minus 3 can be made by the induction hypothesis. So add a 4-cent stamp to that. I just said by can be made, but I mean with 4 and 5-cent stamps. Right. So add a 4-cent stamp to postage k minus 3, and you get postage k plus 1. And that's what we were trying to prove, that you could make postage k plus 1. So postage k plus 1 can be made with 4 and 5-cent stamps only. All right. So that's the induction part of the proof, right? Look at the what you were supposed to do here for strong induction. Show that P of k plus 1 must be true. So that was this. Postage k plus 1 can be made with 4 and 5-cent stamps. Yeah. All right. So that's the induction part. So once you've done the basis and the induction, then you can just write your conclusion and you'll be done. Conclusion. All postages 12 or more can be made with 4 and 5-cent stamps. Only. And that's the proof. All right. Now, something I want to make very clear here because it's going to be a problem on the test. All this writing, you don't have to write exactly this, but you do have to write a lot of words. Okay, you have to write a lot of words. You can't just scribble like something like this. Like if you were doing a proof and you're trying to get points for it, and you're just writing like this, and you just write like k plus 1 minus 4 equals 12 or something. Postage k plus 1 can be made. Right? People try to like condense down all of the stuff into something very, very small. And when you do that, it's not a proof, right? This isn't an algebra problem. We're not looking for a number at the end, okay? We're not looking for you convincing yourself that this is true, right? You need to write the full argument in order to have a proof. It takes a lot of writing. You have to write it out, okay? Now, what I do want to mention, though, on this one is that what I was considering here, why I paused in the proof there, was I was considering just doing this rather than starting here with k plus 1, 16 or more, I was considering backing it up and then just saying at this point right here, just saying like, or even starting up here even, where I would just say, suppose um, k minus 3 is 12 or more, right? Then I would say, um, then postage k minus 3 can be made by the induction hypothesis. So add a 4-cent stamp to get postage k minus 3 plus 4 equals k plus 1. So I thought that it was going to be faster to write it out that way and maybe easier to understand, but then I couldn't decide if it was. And so that's why I just kept going with what I had. But there are like slightly different ways to write it, is what I'm trying to say here. So if you have like a better way to write it, that's fine, as long as you get um, the main things across. All right, so that's another one of those stamp proofs. I did 2 of them because you have a number of them in the homework. All right, let us move on and do a different thing. So in section 5.3, they cover Fibonacci numbers, but I think I want to do it right now. At least one proof with it, because I like to use strong induction, not structural induction or anything like that. So so let's remember what a Fibonacci number is. Fibonacci numbers. You did a lot of them in the homework, right? So you're familiar with them. But so I think I'm going to use lowercase f instead of uppercase f, just because I think it'll be easier for me to write. But so the reason this is in section 5.3 and not 5.2 is because it uses what they call a recursive definition. But we're already familiar with that. So I can just say, let f1 equal 1, f2 equal 1, and fn equals fn minus 1 plus fn minus 2 for n greater than or equal to 2, right? That's the definition of a Fibonacci number. They probably use uppercase in the book, but this will be fine. Okay, and that's the definition that we used in the programming homework as well. So you should be familiar with this, right? So let's just write out a couple of them to convince ourselves how these work, right? So like f1 is 1, f2 is 1, f3, you add up the previous 2. So 1 plus 1 is 2. f4 is 1 plus 2 is 3. f5 is 3 plus 2 is 5. f6 is add up the previous 2, so 3 and 5 is 8. f7 is 8 and 5 is 13, and so on, right? So, you're familiar with those, right? We've seen them before. Now, what we're going to do is, there's a few different proofs we can do. I think I'm going to prove, actually, let me just look in the homework here. There's a bunch of them that actually involve Fibonacci numbers, and I don't know, I just feel like doing a different one. Okay, so I don't know if this one's easy or hard. We're just going to try it. So this is going to be 5.3.12. And like I said, this is not the proof I normally do, but we'll try this one. So we want to prove that f1 squared plus f2 squared plus dot 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 up to fn squared is equal to fn times fn plus 1. And that is for all n. Or for n is positive integer. So for n equals 1, 2, dot, dot, dot. Okay. So this is going to be, I think, easier than the stamp problem, but we will see, right? So let's try this. So proof. And this is a strong induction proof. Okay. So how does this proof go? At least I think it's going to be a strong induction proof. It doesn't hurt to use strong induction when you're supposed to be using weak induction. All right, basis. So what's the basis step? So the basis step is supposed to be showing this property for n equals 1, right? So show, what's the property? This is the property, right? So show true for n equals 1, okay? So that just means put a 1 in on the left and put a 1 in on the right. So if we start at f1 and we go to fn, well, if n is 1, then we're stopping at f1 squared. So it's actually just f1 squared. That's what you have on the right, left. And then on the right, if you put in n equals 1, this will be a 1 and this will be a 2. So f1 times f2. And we don't know if that's true, but that's what we're supposed to be checking. So that's the property for n equals 1. So let's put in the numbers. What's f1? So you have to look it up, right? f1 is 1. So this is 1 squared. And then on the right, you have f1, f2. f1 and f2 are both 1. So that's 1 times 1. So this is just indeed 1 equals 1. All right. Basis step done. Okay. Now for the induction step. You know what? This is not going to be a strong induction. I should have done a different proof. Oh, well, we'll do another proof after this proof, actually. We'll do strong induction. All right. What are we supposed to do? So we're supposed to show that this property up here holds for all n, or holds true for n equals k and any value below that. So assume the formula holds for n equals k, and the strong induction part would be or any smaller n. Right? So that part in the parentheses is what makes this strong induction instead of weak induction. Now, like I said, I don't think we're actually going to use that, but I'm still writing it like a strong induction proof. So what are we specifically showing? Or what are we assuming? We're assuming this, f1 squared, f2 squared, dot, 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 up to fk squared, right? N equals k, equals fk plus 1. All right. And then what we're supposed to do is we're supposed to show that this property holds for fk plus 1. So the way you would do that is, if you remember at regular induction proofs, is if we have the induction hypothesis, then that's usually what you want to start with, but not always. So let's start with that. So start with the induction hypothesis. So I'm just gonna cut it, duplicate it, move it down here. All right, so we're going to start with that. Now, in order to get to the k plus 1 version of this, what would you need to do? You would need to add the next term on the left, but if you add it on the left, you would also need to add the next term on the right. So you add the same thing to both sides. You can't add different things to the left and to the right. We're supposed to be doing valid algebra here. So what do we get? We have f1 squared f2 squared up to fk squared, but now we added fk plus 1 squared. And then on the right, we have fk plus 1 plus fk plus 1 squared. All right, now what we need to do is somehow take this right here and simplify that to where it would look like the right-hand side, but with a k plus 1 in it. So let me highlight this real quick here. This right here, what would this part that I just highlighted look like if you put in a k plus 1? It would look like, oops, not what I wanted. If you took that, it would look like fk plus 1, fk plus 2, right? That would be the next one up. So that's what we're supposed to be trying to get to here. So if we can do that, we're done. Now, what you would do here is you're just trying to do algebra. There's not a lot of algebra you can do here on the right. What I would do is I would notice that both there's a fk plus 1 here and an fk plus 1 here. So I would factor out fk plus 1. So I factor out fk plus 1. And if I factor that out, then on this first term, I'll be left with an fk. And on the second term, I'll be left with an fk plus 1. And then what I would do is I would look at this right here. That's unfortunate highlighting. Hold on. I would look at this right here, fk plus 1, and I would say, well, what's fk and fk plus 1? That's two consecutive Fibonacci numbers, right? So when you add fk and fk plus 1 together, you're going to get fk plus 2. So that's going to be fk plus 1, fk plus 2. And that's actually exactly what we were trying to get to. So we're done with the induction step. So that's it. That's the end of the induction step. As soon as you're done with the induction step, you can go make your conclusion. So what's the conclusion? Well, the formula must be true for all n. And this is one of those proofs that just kind of stops abruptly here. Like you feel like maybe you didn't even prove it, but you did because you did the things that you need to for an induction proof. All right. That's it. Done. Like I said, that wasn't really strong induction. So let me find one that is strong induction. Yeah, all right. So if you write out the Fibonacci numbers, I will. So here's just some Fibonacci numbers. I want to show you something. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. I don't care. Keeps going. What I want to show you, I just wanted to go at least that far because here's a 5 and here's a 55. And if you look at which Fibonacci numbers those are, this one's F5 and then this one's F10. I don't know why I put up 5. This one's F10, right? And it turns out that every fifth Fibonacci number is divisible by 5. So what we want to show is that we want to prove every fifth Fibonacci number is divisible by 5. That's what we want to try to prove. And there's different ways to write that. I think the way the book would probably write it is something like this. So f5n is equal to 5 times some integer. So I'll say like m for all n. That's probably how you would say it. Right, so f5n equals 5m. So the m and the n are not related. But that's how you would say every fifth Fibonacci number. That's just 5 times a number. So 5, like 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15. So f5, f10, f15 is divisible by 5. That means the number that you get for this Fibonacci number is 5 times a number as well, right? So this one's 5, this one's 55. The next one is not 555 or anything. It doesn't go 5, 5, 5, 5, 5, 5, or anything like that. But it will be divisible by 5, just because we're going to prove that it must be. All right. Let's just go ahead and try to do the proof here. Now, this proof is actually not hard, but it requires you to be comfortable with the definition of Fibonacci numbers. The fact that you add one to another one, and you get, like, if you add 2 consecutive Fibonacci numbers, you get the next one. Okay, let's go ahead and just do this proof, and you will see. All right. So how do you start? Basis step. So for the basis step, we would need to show that f5 times 1 is divisible by 5. Right? That's what you would do for your basis step. But of course, f5 is 5, which is divisible by 5. So there's nothing to do there. Just f5 is 5. Done with the basis step. Induction step. You know what? This might not need strong induction either, does it? I'm not sure if this needs strong induction either. It might be hard to come up with one that needs strong induction. They're in the section for strong induction. No, they're in this section for structural induction. Oh well. We're doing them now. Inductive step. So let's just assume that f5k is divisible by 5. Or, right, the other way to write it is like this. So specifically, so assume like f5k is 5 times a number. What number? I could use m. I don't want to use m. We already used them. So let's just say f5k is like 5 c. That's not a c. 5c. You know, where c is just an integer. Some integer c. Now, if this was strong induction, then I would have to assume that f5k, f5k minus 1, f5k minus 2, all of those are divisible by 5, but I don't think we need it. So let's just assume f5k is 5c for some integer c. So f5k is divisible by 5. Now we need to show, now we must show f5k plus 1 is divisible by 5. Right? That's what we need to do for the induction step. So all you're going to do is you're just going to take this f5k plus 1 and you're going to work out what that is. So we're going to start with f5 parentheses k plus 1. What is that? Well, it is f multiply out the 5, 5k plus 5. Now those are subscripts, right? Don't get it's not always easy to tell in handwritten notes, but like these are all subscripts, right? This is not a subscript, but this is a subscript. Okay, so like the 5 can't come off of this f5k plus 5 or anything like that. Okay, so we have f5k plus 5. That's what we have, f5k plus 5. Now what we need to do is actually break this up into smaller Fibonacci numbers. So I'm not gonna, we don't do it with specific Fibonacci numbers here, but off to the side, I'll give you the idea. Like, let's say off to the side, you were talking about f7, right? f7 is just a Fibonacci number. It's not important. But you would be able to say that f7, for example, is f6 plus f5, right? That's just using the rules for Fibonacci numbers. And if you wanted to, you could even take those and split those up, right? Like the f6 could be an f5 and an f4. And the f5 could split up into an f4 and an f3, right? And then that could split up, and then that could split up, and then that could split up, and that could split up. Do you get the idea? I think you do, right? That's what we're trying to do here, but we've got 5k plus 5. So we've got not a specific number here. We've got it just written as 5k plus 5. Nevertheless, we can do this. So we're going to start splitting this up. So you start splitting this up. You say f5k plus 5 is, well, f5k plus 4 plus f5k plus 3, right? Now I'm going to kind of give myself some more space here. Move the equal sign over here. Now what we're going to do is we're going to split these up. So now let's split up the 5k plus 4. f5k plus 4 is going to split into f5k plus 3 plus f5k plus 2. Plus, then you've got this one, f5k plus 3. That one's going to split up into f5k plus 2 plus f5k plus 1. Okay, now I understand that like you're probably looking at this going, okay, well, you can start splitting these up. Every Fibonacci number splits into two other Fibonacci numbers. But you probably don't know, like, well, how far are we going to split this? When do we get to stop? Okay, and well, you're just going to see me do it, and then you'll see when we get there why we've gone far enough. And I can show you where far enough is, by the way. Far enough is we assumed that f5k was divisible by 5. So we need to get these down to f5k's, right? We had 5k plus 5, now we got 5k plus 4, now we got 3s and 2s, 2 and 1. We need them all down to basically 5s. 5k plus 0s. That's not the whole story, but we'll see. So let's keep doing this. So 5k plus 3 is 5k plus 2 plus f5k plus 1. Right, that's this one. And then the next one, 5k plus 2, is 5k plus 1 plus f5k. And then we got another f5k plus 2. Oh, were those both 5k plus 2s? Yeah. I could have combined them, but I didn't. It's fine that I didn't, by the way. So that's another f5k plus 1 plus f5k. And then we got an f5k plus 1. Okay, let's just leave it like that. Now I understand, like you can probably see that what's happening here is we had 1, 2, 3, 4, and we split that one into 2. This one got split into 2. This one got split into 2. And if you look, I didn't actually do anything with this one. This one I just left alone. Okay, that's because what I want to do is I want to get it down to, oops, what? That's not what I wanted. I want to get it down to 5k plus 1s, 5k's, 5k plus 1, 5k's, 5k plus 1s. Those are what I want to keep. Why does it keep going to, okay, I don't know, 5k plus 1. So that's what I'm trying to get to. I want all the values that low. So I still have one more to split. So let's split that last one, the f5k plus 2. And I'll get f5k plus 1 plus f5k. And then I've got all the others. So I'm just going to write them. Could I copy paste them? Wait, I could, huh? All right. So the first one splits up the way I've got it, and then I'm going to try to copy the others. Duplicate. Kind of off. Didn't leave enough room. Okay, let me try again. Starting to feel like it would have been faster just to write it, but permitted. Okay. So this is what you get when you split that last f5k plus 2. But something happens now if you actually combine your terms. So count them up here. So let me just erase the highlighting. So count them up. So I've got f5k plus 1, f5k plus 1. I wrote just k plus 1, but that's a 5k plus 1. Another 5k plus 1, another 5k plus 1, another 5k plus 1. How many are there? 1, 2, 3, 4, 5. So there are 5 f5k plus 1s. All right. And then the other terms that we've got here are what? Looks like there's 1 f5k, 2 f5ks, 3 f5ks. So 3 f5ks. All right. So I just combined all my like terms there. Now what you want to do now is apply the induction hypothesis, which we haven't used yet. Use the induction hypothesis. So the induction hypothesis, what was the induction hypothesis? The induction hypothesis up here was that f5k is 5c, right? Because f5k was divisible by 5. So it's 5c. So 5 f5k plus 1 plus 3, and then like 5c. And the reason you want to do that is because now look, you got a 5 and you got a 5. That means you can factor out a 5 and have f5k plus 1, 5k plus 1, plus 3c. And look at that. That's divisible by 5, right? That's 5 times an integer, which is divisible by 5. So what we showed there was if f5k is divisible by 5, then f5k plus 1 must also be divisible by 5. Right? And that's what we were supposed to do for the induction step of this proof. So we're on to the conclusion then, which is just f5n is divisible by 5. That does not say divisible. By 5 for n equals 1, 2, 3, dot, dot, dot. And there you go. That is your proof. Okay. Now that's a really common proof. A lot of times I put this proof on the test. And so I'm not guaranteeing that I will this time because you guys have a take-home test and that's unusual. But, fair warning, you should spend some time understanding this proof. All right. So I think that should be it for right now. I think it's been 50 minutes. So what we're going to do in the next lecture is we're going to move on and we're going to look at what they call structural induction, which this was actually in the structural induction section. But we'll do that, and there's something involving like triangulating polygons that we didn't cover yet. Um, so that's technically from 5.2. But so what we did kind of was we covered some of 5.3 now, and in the next section we're going to have to come back and cover part of section 5.2. So I kind of switched the order of two topics, but that's okay. Won't kill you. All right. So that's it for now. I will see you next time. Where is my mouse so I can stop the video?